Welcome back to ECE 441A, 541A. Our Tech Elective Information session is today or tonight at 5:30 in room 530 if you're interested in what's being offered for technical elective courses and the Accelerated Master's program if you're interested in that. Homework number 4 is due on Monday. Homework 5 is due the next Wednesday, 2 days apart, so you're going to have to start really working on these homeworks. And then exam number 2 is a week from Friday. That's why we're having those homeworks stacked up. We want to cover all of that material, and there should be practice material for exam number 2 on D2L. Then there's no class on the following Friday, the 28th, and lab number 2 is due the following Wednesday. And lab number 2 material is going to be a part of exam number 2. Similar to exam number 1, you need to know the information on lab number 2 to perform well on exam number 2. What I want to do today is help you get started or speed right through homework number 4, hopefully by providing you with some interpretation of the wording of homework number 4, some of the problems. We will return to our settling time examples and then start with steady state air. And it's important to get these concepts well in hand because they are connected and they are a part of the subsequent material. One of the first problems on homework number 4 is problem P 4.6, and it has 3 different parts, A, B, and C. And the first question is determine the sensitivity of the system. And maybe it's not clear what the system is since there's 2 different inputs and 1 output. I'm telling you the system that he's referring to, or I'm going to assume he's referring to in problem or part number A, is between the speed setting and the actual speed, or that's what I'm calling T sub 1. And you're now trying to find the sensitivity of that transfer function with respect to one parameter, and that parameter is K sub E, which is in the numerator of your engine and vehicle dynamic equation. So find the transfer function, T sub 1, and then start doing these sensitivity problems or to finding the partial to find S of that transfer function with respect to K sub E. T sub 1 is between the speed setting and the speed. So it's the transfer function, you're saying V of S over R of S is T sub 1. And to find these transfer functions, you can set the other inputs to 0. Because they're linear systems, superposition holds, and if you're interested in how one input impacts the output, you can set all the other inputs to 0 while you're investigating that one. And in this case, you would be setting or not even considering T sub D. The reason it's highlighted in yellow is because the next part says determine the effect. Well, by effect, let's just find the transfer function between T sub D, or delta T sub D. That's just an input. He's just calling that an input. You could just view that as a disturbance D, but he's labeling it delta T sub D. You want to find the transfer function between delta T sub D and V, and that's what I'm now calling T sub 2, and that is the effect. And delta T sub D is just an input. Part B, all you're doing is finding a transfer function. You're finding the effect. Part C is now, this is a speed control device, and you now are trying to find at what setting or at what load torque will you actually, if you start now going up that load torque, will you stall? That's part number C. And in this case, you want to have the impact of both inputs, and because of superposition, you can add up those two pieces. You found the first piece in part A, the second piece in part B. Now he says, okay, assume you're going 30 miles an hour. That's a constant, so that's 30 over S. I think it's in miles per hour. It doesn't matter the units. Let's just say it's 30 over S. He wants to know, when does it stall? That means your velocity will be 0. And now you are trying to find this constant number, delta D, that satisfies this equation when it's equal to 0. That's part number C. And that maybe wasn't that clear from the problem statement. Determine the constant percent grade, that's the delta T sub D, where it's really just the delta D in the delta D over S for when the vehicle stalls, and that means your velocity is 0. Yes? Oh, it is? It may be. I need to look. So the question was, is problem 5.4 missing from the problem statements? And I'll go back and look and see. Maybe I didn't scan that. I knew I was getting in a hurry when I was scanning that. Thank you. Problem 4P4.7 is another block diagram, and the effect of T sub D on Y of S, based on what we talked about in the previous problem, I think you now know that's going to be this transfer function between T sub D, and now he doesn't include the delta. Go figure, it doesn't matter. He was just including that delta together with T, and you could just call that all just 1, or you could just say T sub D in the previous problem. The effect, again, is just finding this transfer function, and you can do that with Mason's gain or block diagram algebra. That shouldn't be a problem. Then you need to find the sensitivity of the closed loop to K sub 2. Well, now the closed loop is not the transfer function you found in part A. The closed loop is between the reference input, R, and the output, Y. And once you've found that transfer function, now you perform this sensitivity expression of T1 with respect to K sub 2, and you now have to find where K sub 2 is in this transfer function T sub 1 and take all of these partial derivatives to compute the sensitivity. And then you're asked to find the steady state error. When the reference input is a unit step, essentially, the disturbance is 0, and now they want to know if you put in a step command, let's say that's the desired joint angle, where does the actual joint end up? What's the steady state error? The output Y is related to the input by the transfer function T1. We're assuming the disturbance is 0. And now the error, it's not going to be right here, per se. It's actually going to be just the difference between R and Y. You now compute E as R minus Y. The reason this is not in that same point coming out of the summing junction is because there's some dynamics in the feedback path. Compute your error as the difference between the reference and the output, and then if you want to look at what happens in the steady state, this is why you learned your final value theorem. You can apply the final value theorem and examine this expression, capital E of S, the limit of that times S as S goes to 0. And that will produce your steady state error. Question? Is there a general rule for the error? I wish there was, but you just have to understand what's being asked, and I'm telling you now what to assume. In this case, the error, it's not really lay down in step C. It just says the steady state error, and so you could maybe call that anything, but let's assume to be consistent that that's the difference between where you want this angle and where the angle actually ends up. And that's what we're defining our error. So that's r minus y. You can find an expression for y in terms of r. You've got that transfer function. You can plug that in to this expression for y, and now you have e as a function of r, and you know r is 1 over s. So you can calculate that from that expression. Problem P 5.6. Again, it's asking for a steady state error, and its E is R minus Y. This is now maybe you have a robot welder, and this robot is trying to follow this sawtooth type pattern. And ideally, you would want your end effector on the robot to be pretty close to where you want it to be. You don't want there to be a huge error. You're now welding something that's not even near the joint between the two pieces of whatever you're welding, if it's a big error. So we're hoping if this is where we want to be in terms of the green sawtooth, hopefully we will get close to that. And that's why we're after the steady state error. But you're going, well, you're never in a steady state. You just keep bouncing back and forth. So that's what we have to get comfortable with now. And figure 37 in chapter 5 talks a little bit about that. And here's the picture that you might start thinking about in terms of a steady state error. Here the command or the input is dashed. That's where you want your, let's say, position to be. And your position is actually this solid green curve. And the steady state error is defined once you've reached or settled, or once you've passed really your settling time. Here is where an infinite amount of time isn't very long, you hope. Right? How long is infinity? 5 tau, 5 time constants. So if your tau was a millisecond, infinity now is 5 milliseconds. After 5 milliseconds, you're now at steady state. And in this particular picture, I hope you can see that, oh, about this time, we've reached a consistent difference between what we've commanded and where we actually are. And that's now the steady state error. Then you turn, and obviously there's transient. After you've made an adjustment in your input, and you now have to say, oh, if I'm looking for the steady state error in this second interval, I need to wait a while. Maybe I'll just call it at 5. Or maybe you'll call it at 5.5. They should be the same. If 5 is far enough in or after an infinite amount of time, not theoretically, practically, which is 5 tau. Is that clear? So even though you're bouncing back and forth in this sawtooth, you now have to wait until you're settled, you've passed your settling time, and then you can start worrying about your steady state error. And if you want, there's the MATLAB commands that allow you to compute or really create this figure. You don't really have to create that figure. You simply have to compute E and use the final value theorem. And what you're really doing here is you're saying, oh, if I'm using the final value theorem, I'm pretending that just goes on and on forever, and my steady state error is doing something like that. And hopefully, if this was drawn accurately, what's happening at 9 is the same as what's happening at 12, at 30, if you pretended that it just went on forever. That's why you can get away with using the final value theorem. You're going, well, the final value theorem is what happens at infinity. Well, now you have to interpret what is infinity. And it's when you're beyond that settling time. Now, you should be able to knock those problems out in about 10 minutes, as long as it takes you to write. I'm joking a little bit. It may take you a little bit more than 10 minutes to solve those problems. But this should help you not struggle with the wording and the interpretation. Let's now return, since we've been talking about when is an infinite amount of time, not very long. That involves this settling time, and 5 tau is 1%, 4 tau is 2%. And it really doesn't matter that much. But in this textbook, we are typically using a 2% settling time. So let's look at where we were last time with our settling time sort of exercise that we stopped the class with. We had a plant. That was our system dynamics, G of S. We had it interconnected in this feedback pattern. And now we do not have any dynamic behavior in the feedback path or any dynamics. And so the error, in this case, if it's R minus Y, the error, in fact, is right there. And you could now find the transfer function between R and E, if you wanted to, from the block diagram directly. Let's assume now that we have a reference input of a unit step. In the frequency domain, that's 1 over S. And let's compute the settling time for 3 different systems, just to start to get some insight into what's going on with a system and settling time. A, I think we did on Monday, in Monday's class. We have a constant in the numerator, and this is now a transfer function in time constant form. The time constant is t sub 0. Our time constant is 1 second. Our gain is 10. And what's the DC gain of that transfer function? K sub 0. Since it's in time constant form, it makes the DC gain just drop right out, doesn't it? We're letting S go to 0. And we have now G of 0 as the DC gain as K0 over 1, or K sub 0. Since we've normalized the denominator constant to be 1 to get it in time constant form. In plant A, or system A, we had this relationship between our time constant and our gain. Now we have a similar relationship. There's still a factor of 10 difference between T naught and K naught, but now the gain is not as big. What's the DC gain in plant B? It's 1, isn't it? What's the time constant? It's 0.1, right? Tau naught, it's right here. I gave it to you. That's why you're going, why is he asking? Why is he asking for the time constant? It's right there on the board. Can't he read? No, I don't have my glasses on, so I can't read. So you need to help me. But there, the time constant is 1/10 of a second, and the gain is 1. The DC gain is now 1, but the ratio of the time constant to the gain is the same in A and B. Okay, just trying to get a feel for what we have. And now for C. That one's completely specified. There's no variables in that one. What's the DC gain of G? It's blowing up, isn't it? It's unbounded because we have this integrator at the origin. We have a pure pole, or a pole right at the origin. The integrators always are a pole at the origin. We have one pole at the origin, and we'll call that a type 1 system. But this one now has much higher gain at DC than these other two. Now let's compute the settling time from before. Here's where maybe some of you, when I gave you this, we had a disconnect. I said, what's the settling time? And some of you might have said, well, he gave us G of S, and there's the time constant. But now, remember, this is in a closed loop configuration. Now we have that plant. Its output is fed back compared with the reference input, and that air signal now drives the plant. Meaning we've changed the dynamic behavior of our open loop system plant in this closed loop configuration, and that's going to change our settling time. In the open loop, what would the settling time of plant A have been? If we disconnected the feedback, what would the settling time be, the 2% settling time? How many time constants is the 2% settling time? 4. What's tau? In A, in case A, it's 1, so what's the settling time? 4. But we're going to calculate it to be much quicker than that because we've now sped up the system with feedback. And the way that we're doing that is finding the closed loop transfer function, which is our cheer, G over 1 plus GH. H was 1. We now have G over 1 plus G. We plug in the G, which is there's G and there's G. Now we have a ratio of ratios. That's not what we typically want to be dealing with, so let's get a common denominator in the denominator. Put everything over tau naught S plus 1. Cancel the denominator and denominator and the numerator and denominator. Can I make that even more complicated? Hopefully nobody's walking by the door, right? What is that guy talking about? But now you can clean that up and just get a ratio of polynomials, where you now have K naught over tau naught S plus 1 plus K naught. By canceling those two, the denominator and the numerator with the denominator and the denominator. Now we can find our settling time from the dominant pole, or poles. How many poles do we have? Whoops. Were you quick? You only have one, don't you? You have one S, S to the 1 in the denominator. You have a single pole. That's going to be real. It's on the real axis. Now we don't have to worry about angles, do we? What do angles give us in terms of transient behavior? Design specification. The angle theta is related to zeta, and zeta is that figure 5.7. When I start saying this, you need to just be visualizing not just tubes, but zetas and thetas, right? And what's zeta associated with from figure 5.7? Percent overshoot. So you shouldn't be expecting a percent overshoot, should you? If this is a first order system, if this is an RC circuit, how's your response behave? Exponential. It doesn't ring, does it? It's just going exponentially up to its final value. That's what a first order system does. And we can find that pole location by setting the denominator equal to 0, and with T naught or tau naught equal to 1 and K naught equal to 10, we ended up with that single pole off into the left half plane, which is good. What does that mean? What's our system? It's stable. We have a negative exponential, and it's now e to the minus 11t. And what's sigma? If our pole is at minus 11, what is sigma? I'm asking some really hard questions. It's 11. I know it's Wednesday, not even Friday, and I'm asking these easy questions. Don't you hope that's true in a week and a half on the 21st? Yeah. Good luck with that one. So now you have 4 tau, 4 over sigma, 4 over 11. Now you might need your calculator. Hopefully you don't lose it. And you now have 4 over 11 is now what? 0.3636. What's that compared with? What was the open loop settling time? 4. Now with feedback, we've reduced our settling time by more than a factor of 10. That's the power of feedback. Or that's one of the reasons we use feedback, is to help change the dynamic behavior of our system. And we've done that, and we've demonstrated it here. Pardon? So now the question was, with a quicker settling time, do you have a better system? Maybe not. That's why you're coming. If that was as easy as it was, which is a good concept, but if it was that easy, you guys wouldn't be in this class. You would just be going, crank that thing up, get that pole as far off into the left half plane as possible. I want as fast a system as I can get. But what's that mean? That may mean you need a lot of energy to get your system to move that quickly. And maybe you don't have that ability. Maybe you don't want to hit your system that hard. You hit it that hard and maybe it breaks. So even though, remember that crosshatched section of allowable region in the S-plane, somebody's going to get smart on me and say, I just made mine minus infinity plus and minus j infinity. That's where I put my pole. That's in the allowable region. Yes, it is, but it's not physically realistic. So there are bounds. We can't go too far into the complex S-plane. And that depends on the system, and that depends on your engineering understanding of what you're dealing with. And in some cases, you may have to make this trade-off. You may say, oh, well, I don't really need it to be 0.36. I just need it to be 2 seconds and not 4. And we'll learn that in this case, we could have just reduced our gain, K0, to make that happen. All right, now let's keep going. Plant B had the exact same structure, just different values for tau0 and K0. In this case, we get exactly the same expression for our transfer function, and we want to find the settling time, which means that we're interested in finding what? If we're interested in settling time, what are we going to need to find? Our pole. What if we had 10 poles down there instead of 1? We would look at the dominant pole. Is everybody comfortable with the dominant pole? In this class, we'll just assume that that's the closest one to the origin. And if they're complex, now that we're looking at the hypotenuse, how far are we from the origin? We'll take the dominant one, or the dominant pair. They will play together as a whole, but if they're widely separated, the dominant pair are just the 1 or 2 that are closest to the origin. In this case, we only have 1 pole, and we can now solve for that. We now have 0.1s plus 2 equals 0, and this is why you took 3 semesters of calculus and a differential equation, is so you can solve this first-order linear equation. Don't tell your mom and dad that. They'll be upset. Huh? This is now 0.1s is equal to minus 2, or s is equal to minus 20. And now what's sigma? 20. Settling time is 4 tau, but tau and sigma are reciprocals. And this one's even faster, isn't it, in terms of settling time? The first one was 0.3636, I think. This one's now 0.2. The gain wasn't as big, but our time constant was shorter in the open loop, and our pole was where relative to the A system? Where's this pole in B? A was at minus 11, B was at minus 20. We're going further into the left half plane. We're getting faster in terms of our system behavior. All right, let's do C. And no, I just heard somebody play a middle C. No, sorry. We've got some people out in the hallway. They're listening in. They're wanting to hear that hypotenuse and angle and denominator. C. Plant C was G of S was 1 over S plus 1. Now you know the steps. We can't just play with G because it's in a closed loop configuration. We need to find the closed loop transfer function between the reference input and the output Y. That's now because we have unity feedback, output feedback. It's G over 1 plus G. Again, we have this ratio of ratios, but we can clean that up. You know that we'll cancel the denominators, and now we have S plus 1 for our closed loop transfer function. And we can multiply this out. We have S squared plus S plus 1. And if you're interested in where those poles are, you can factor that. You could get out your calculator and do the quadratic formula if you wanted to, but you're going to start seeing this. If we completed the square, that would give us our S squared plus S piece. And now we have 1/4, and what do we need plus 1/4 to get us 1 when it's squared? Three-fourths. So we take the square root of 3/4 and we get the square root of 3 over 2. Now where are your poles in this system? Based on this factored form. Why did I factor that into that form? Because the poles are jumping out at you now, right? They're at minus 1/2 plus and minus j square root of 3 over 2. Now what can you say about the angle? Is there an angle? Yes, and you could calculate it. And once you found that angle, you could find the cosine of that angle, and that gives you zeta. And now you can go look at figure 5.7, or you could plug it into that formula and you could find your percent overshoot for a given zeta. But we're not asking for zeta or percent overshoot. We were after settling time. That's 4 tau. 4 tau, but we had a real pole before and we knew what sigma was. What's sigma here? What's sigma if it's now this distance, isn't it? This is now our sigma. Is that clear from those poles? So we now have 4 over sigma, and sigma now was 1/2. Our settling time is 8 seconds. What? We put this in a feedback interconnection. Well, we had an unstable system because we had that pole at the origin to begin with, open loop. And now we have, what, an 8-second settling time. So why do we want that integrator? Who knows? But we have it. Sometimes you just have it. When did you have an integrator in a transfer function? What would this transfer function maybe be representative of? What kind of a system? What could you just think about if you saw that 1 over s times s plus 1? DC motor. The angle is the output, and the input is a voltage. And if you wanted the angular velocity, that s wouldn't have been there, would it? You would have been having the angular rate, and then we would just have this 1 over s plus 1 as a, let's say, a normalized DC motor. Question? So now, no, I'm saying that this 1 over s times s plus 1 you could think of like the physical dynamics of a DC motor. And that 1 over this s term is like integrating the velocity so that now you're getting position. So if you just had, maybe I shouldn't have mentioned that, but I'm trying to get you thinking about this g of s in terms of something other than just an abstract transfer function. 1 over s times s plus 1. Now you have a pole at the origin and another pole where? At minus 1. And that's your open loop, and we'll start learning what that means. But now with feedback, we've moved those. They started here and here. And they moved with feedback to stable and with the sigma of 1/2. Now, what I want to do, now that we're thinking, settling time, let's think about steady state air. Here's a question. Whoa, this is busy. Which system, blue, red, or black, A, B, or C? I was trying to color code this, so if you were really thinking of, and don't play with me in terms of colors, okay? This is A, B, and C. Hopefully I got these correct. A was our first plant, 10 over s plus 1. B was our second plant, and C was our type 1 system, our third plant. And now I want to know, and here were the respective settling times, 0.36, 0.2, and 8. The question of all questions, now you have to get your die out and roll your die because there's 6 choices. Not as easy as flipping a coin. Your odds have been reduced, haven't they? I want you to just maybe guess at this point, based on what you know, which system gives you the best steady state air. And now I'm saying that if we go back to this, we want to know which system gives us the smallest E in the steady state. After this is settled, after the settling time, which E will be the smallest for these 3 plants, and which will be the biggest or the worst? That's what I'm asking here. Does everybody have their guess? Have you done the random generator algorithm in your head so you didn't have to pull out your die and throw it on the ground? Oh, here. What did we come up with? Any ideas? How many think it's 1? A is the best and B is the worst. A, B. Okay. Number 2. A and C. Is anybody thinking? All right. 3. B and A. I think I needed to ask you, and you needed to show me digits, huh? Some people are thinking 3. How about 4? What is 4? B and C. So B has the best, and C has the worst. Okay. How many said that? That was 4. 1, 2. Boy, you guys are quick. Your settling time is too fast. Remember who's up here? Right? All right, I saw about a half a dozen hands, didn't I? So I'll say 6. Whoa. Let's change that color. How about 5? C is the best and A is the worst. 5. C is the best and B is the worst. You vote. You stuffing the ballot box? Well, you could be wrong. 1, 2. I saw a few more, didn't I? Maybe 10. Well, actually, this is the right answer. So let's look at where that's coming from, or why that might be the case. And let's just now start talking about what we mean by steady state air. What is the steady state air? And I hope after today you are comfortable with that. Do you remember seeing something like this in the lab? Maybe yours didn't have this much difference between the reference, which is the red, and the actual position, which is the blue. But does this sort of look like what you might have measured in the lab? Do you see why we can talk about steady state? Now we are dealing with what's happening right there. And then it switches again and we're after this. Or we're after this. Wow, was this consistent? The steady state air? Not really, was it? So now if you had to go into your boss and say, and she asks, what's the steady state air? What would you do? Probably give her the largest one, right? And then you guys decide if that's acceptable or not. But you understand what we're talking about when we say steady state air, where this is really never going to be in a steady state as far as high, low, or 2,000 counts, 0, 2,000 counts. But infinity's not very long, is it? And this is open loop. Infinity is less than, well, I should have put that in time, but it's probably about a half of a second in the lab. Another one is this sawtooth, and we've talked today about steady state. Where in time would you maybe start looking for the steady state determination in this figure? Pick a time. Now you have 0 through 8. Get out your 8-sided die and roll it. When would you want to look for, at what time would you tell somebody, choose that time and that'll be our steady state air? Everybody get that? Does that look okay? Maybe even like right in there, maybe. What? Is it? Oh, those yellows aren't showing up very well, are they? That highlight. But do you see what I'm saying, or trying to get you to think? It's this distance is your steady state air. Between those two, that's your steady state air. The R is red and the Y is the black line. And now you're at some particular point in time, you calculate their difference and that will be your steady state air. But you want it to be settled by the time you start calculating this steady state air. Now to determine, you can memorize that for exam number 2. That's your MATLAB code to generate that figure. And I'm going to provide this for you so you can memorize it for exam number 2. I don't think that's what I want. I don't need you to be memorizing. When we are talking about steady state air, what are we assuming? That's what I want to, that's the question I want to address now. It's pretty vague, but let's see if we can come up with some ideas as far as what are we assuming when we start talking about steady state error in these two situations and in general. One, what are we assuming happens with our system? That was vague too, wasn't it? What do we need our closed loop system to be in order to even be talking about a steady state error? It has to be stable, doesn't it? We have to have settled. So the first thing that we are assuming is the closed loop system is stable. And in general, you're going to have to check this to begin with, or you can't even apply the final value theorem. If I give you a case where the closed loop system was actually unstable, and I sort of trick you and I say, give me the steady state error, and you plug in the final value theorem and you get a number, but your system wasn't stable, what's right or wrong about that number? It's wrong, isn't it? What? Everything's wrong with that number, isn't it? So you need to verify stability to begin with. And how do you verify stability? We check the poles, don't we? So here our check would be roots of the closed loop, not necessarily the open loop, because you may be in a closed loop configuration. Check the roots of the closed loop denominator polynomial. That's one thing that we're assuming. Another assumption that we are making, number 2, is we are assuming that with the transients have died out. They're gone when we start calculating the steady state error. The transients are gone. Before we change the reference signal. Now, what do I mean by that? Suppose that I now have a reference signal that looks like that. Here's my reference signal. What's that second assumption saying? Can I be any more vague? Here's the time axis. The transients are gone before we change the reference signal. Here's how long we are sitting in this pattern. So let's call that Tref. And what am I meaning? And so this might be, let's assume that it's a square or symmetric, and these are all the same. First, our system has to be stable, doesn't it? That's assumption 1. And now we're assuming what relationship relative to time and Tref in our system. The settling time of our system, of our closed loop system, needs to be less than Tref, doesn't it? That's what we're saying, or we can't even talk about a steady state error. If our system was bouncing around all this time between after you change Tref and then you change it again, and it never settles, you don't have a steady state error, do you? Those moves are patented. The university is very interested in property, intellectual property, and so those particular moves, and I apologize for those of you listening, you don't get to see some of this, but now what number 2 is saying is that T sub S is less, the settling time is less than Tref. And the other assumption that we're doing when we're using the final value theorem is we are actually treating the first time segment, and bear with me for just a few more seconds, we're treating the first time segment of the reference input as if it went on forever if we're applying the final value theorem. But we know as long as we've reached the settling time, we can now transition and we can do it again. But we treat the first time segment of the reference input as if it goes forever. And we'll pick up at that point on Friday, maybe with a new topic, but we'll see. Stay tuned.